honor, including the Maluna Azad National Fellowship and SCRB IUSSTF Fellowship, the latter of which enabled him to further his research at San Diego State University. Dr. Ferrado's work in understanding autism spectrum disorders through advanced neuroimaging techniques has received international recognition, highlighting his dedication to bridging technology with healthcare solutions. Beyond his research, Dr. Ferrado is a passionate mentor and educator, inspiring the next generation of engineers and scientists to push the boundaries of innovation in biomedical engineering. His expertise and insights are invaluable, and we are privileged to have him with us today. So, with great enthusiasm, let us welcome Dr. Ferrado onto the stage. Welcome, Lucy.
Professor Kavita, so for inviting me over here. So she is my senior from 2008. We are actually collaborating. I was doing my master's and she was doing PhD. So we had an opportunity to work with her, and her friend is my first mentor. So today's talk, I would like to actually cover a few topics like nervous system, brain, so brain, spinal cord, neuron, action potential, neurotransmitter, how you can actually measure the brain activity using EEG, epilepsy prediction using EEG signal. That is one of the studies we are actually working on. And then how brain imaging can be actually occurred, and then how we can actually diagnose ASD, that is my actually research area. So we can actually see over here the nervous system that can be actually classified into actually a central nervous system and also the peripheral nervous system. So the central nervous system actually has brain and actually spinal cord. That is our actually function unit of our body, and the brain consists of actually nerve cells called one of the nerve cells is actually the neuron. On the other hand, actually we have the peripheral nervous system, so that is actually a somatic nervous system and actually autonomous nervous system. So in the case of actually somatic nervous system, all our actually voluntary activities. So voluntary activities means actually hand up or actually walking, so that are actually we are controlling these activities. So on the other hand, actually autonomous nervous system, the control is not with us. It is actually automatically happening, like actually our heart rate, lungs, excretion, digestion. So that actually comes under actually this actually autonomous nervous system. So then it has actually other two parts like an actually sympathetic and actually the parasympathetic. So the parasympathetic is actually our abnormal actually activities. Like if you are actually embraced, automatically you will be having actually sweat, or if you are actually running, so your actually heartbeat actually increases. And then actually body adopts to actually become actually again to the normal condition. So sympathetic is actually our actually the normal actually condition. So our actually nervous system, so these neurons are actually connected between this actually central nervous system and the peripheral nervous system in order to do a function. Suppose we are actually seeing an actually an image or actually a person. So it actually falls into our actually retina, then it actually goes to our actually visual cortex, then it actually goes to hippocampus. So this actually recollects whether this person is actually known person or not through actually memory, and then it actually gives the information to motor cortex. If it is a known person, you will raise your hand and you say hi. So all this actually communication happens because of this actually neurons are actually connected and they are actually communicating actually with each other. So we are actually interested in actually one of these actually nerve cells. There will be actually a number of many actually nerve cells are there. So one of the nerve cells is actually the neuron. So we are actually interested to know how the neuron actually works. So here is actually the diagram of an actually neuron. I think the pointer is actually not able to actually in the LED screen. So I can actually explain over here. So it has an actually dendrites, so that helps to actually receive the signal from the other neurons. And then it has an actually cell body, it actually organizes all these actually the whole functional unit, and then it has an actually a nucleus that actually controls this actually entire neuron. And then we have an actually important actually part, so which is called as actually the axon, that helps to actually transfer the information from the cell body to this actually axon actually terminal to give the information to the next actually that neuron. So in the case of actually axon, we have an actually a myelin sheath, so that actually protects this actually neuron or actually serves an actually an insulation. So the signals actually transferred from cell body or the axon terminal should not have any loss. So it actually acts as an actually insulation. And in the case of actually peripheral nervous system, so throughout our body we have actually the peripheral nervous system, and the brain and the spinal cord we have actually the central nervous system. So in the case of actually peripheral nervous system, it is this actually myelin sheath is made up of Schwann cell, and in the case of central nervous system, that is brain and actually spinal cord, the neurons is actually the myelin sheath is made up of actually the oligodendrocytes. So now we have an actually an interesting question, like why actually the brain is actually having two colors, like actually an outer gray matter and an actually inner white matter. So why it is like that? So this actually myelin sheath, so it is actually made up of actually white. So this part of the neuron that actually looks like an actually white color when we actually take an image, and this actually whole actually cell body, it actually looks like an actually gray. So what we are having an actually gray color over here. And the case of actually brain, so inside this actually region is actually white and outside is actually the gray. And the case of actually spinal cord, it is actually ulta or actually the vice versa. So inside it is actually gray and outside it is actually white. So we are interested to know how an actually a neuron actually fires, or actually how actually the neuron transfers the signal from this actually cell body. So neurons actually cell body through an axon to axon terminal. So the communication or the transfer of signal from this cell body to the axon terminal through the axon is called as action potential. And when it happens, so we are interested in it. So you can see over here, so outside the cell, a diagram depicts the outside the cell and inside the cell. Let's assume that it is an neuron, and extracellular space and intracellular space is over there. And you can see over there are ions are there. So maybe few examples are given, like sodium ions may be there, chlorine will be there, potassium will be there. These ions will be present inside and also the outside these cells will be there. And so these ions can move inside and outside the cell. So they can diffuse through this cell membrane is over there. So they can diffuse through this cell membrane. And they can come inside and also it can go outside this cell. So initially, let's assume that there is no neuron firing is there. So neuron is in the resting state potential. So you can see over there will be more number of sodium ions outside this cell, and there will be more potassium ions inside this cell. So this can be having a difference in ion concentration. So that is called as an chemical gradient. So on the other side, so you can see over here, so there will be more positive charge on the outside of the cell when compared to the inside of the cell. So that is called as an electrical gradient. So because of this ion concentration and the electrical concentration difference, you can call this as an electrochemical gradient in the third image over here. So at the resting state potential, so inside this cell, it is minus 70 millivolt less when compared to the outside. So what it is in the graph, so it is showing like minus 70 millivolts. So that is the resting potential. That what it means is, so inside the cell there is minus 70 millivolt less when compared to outside the cell. It won't come back. The LED it won't break the point. So you can see the first diagram. So there are few ion channels are there. So I said the ions are present inside the cell and also the outside the cell. So they can't freely diffuse between these cell walls. So there should be some ion channels are required in order to diffuse these ions outside the cell to inside the cells, or inside the cells to the outside the cells. So there are called as ion channels. So there are three ion channels are there. One is a voltage gated ion channel, another one is a ligament gated ion channel, and another one is a mechanically gated ion channels. So these voltage gated ion channels will open or close if there is some potential difference is there. So there should be an minimum potential difference should be there. Then these ion channels either will open or close. So in the case of ligament gated ion channels, so they will open or close if there is neurotransmitter is binding on this ion channel, then it will be opening or closing. So in the case of mechanically gated ion channels, if there is a difference in the length or pressure on this surface of this cell wall, so then it will open or close. So you can see over there, because of there is the third image, because of some length or pressure difference, this ion channel, mechanically gated ion channel may be opening, and there is few ions may be coming inside. Let's assume that there is sodium ions are coming inside. So these sodium ions are positively charged. So there will be more positivity will be there. So there is it moves from minus 70 to around maybe minus 65 millivolt. So this small difference in potential is called as graded potential. So once this actually graded potential is actually happening, so again it should actually come back to an actually a resting state actually potential. So how it actually come back to the resting state potential? There will be actually a sodium potassium pump will be there. So this sodium potassium pump may be actually opening. So it will be actually keeping 3 actually sodium ions inside and 2 actually potassium actually ions outside. So that makes actually a normalize this actually condition, and then it actually comes to an actually resting state actually potential. So now how this actually neuron firing actually happen? So that we can actually see over here, like, so if there is actually more actually sodium potassium pump is actually opening, so or actually if there is actually change in the length or actually pressure of this actually neurons is actually happening, or actually some actually neurotransmitters are actually binding to these actually ion channels, there will be actually more actually ions may be actually coming inside. So if there is actually more ions are actually coming inside, so this will actually cross an actually potential of actually around minus 55 millivolt. That means that more ions are actually coming inside this actually cell, so it will become actually more positivity. So it actually goes from minus 70 millivolt to actually minus 55 actually millivolt. That means first time it was actually more negative, so more ions are actually positive ions are coming, so it becomes actually positive. So minus 55 millivolt it actually comes. So what happens actually minus 55 millivolt is actually comes. So this actually voltage gated ion channels, that may be actually sodium actually ion channels actually get actually activated. So these voltage gated ion channels can actually open or close. If there is actually some actually ions actually voltage is actually difference is actually there. So this actually sodium actually ion channels will actually open. So more actually sodium ions will actually come over here. So that actually makes this actually more positivity inside this actually cell. So that actually leads to an actually potential of around actually 30 actually millivolts. That is actually plus 30 millivolt it actually goes. So more ion channels are actually coming, more ions are actually coming, that is actually positive ions are actually coming. So more actually positivity inside this actually cell. So it actually goes to actually plus actually 30 millivolts. So this phase is called as actually a depolarization. So once it actually reaches this actually plus 30 actually millivolts, what happens is, so this actually sodium ion channels actually get actually closed. So initially it was actually open, so then it actually get actually closed. So when actually this is actually closing, this actually potassium actually ion channels get actually open. So this actually potassium ions actually goes outside this actually cell. So actually what happens? So the positivity inside this actually cell will actually reduce, that leads to actually from plus actually 30 millivolt to it actually comes to actually around actually minus 90 millivolt. So why it actually goes to actually minus 90 millivolt rather than actually minus 70 millivolt? So the resting potential was actually around actually 70 millivolt, right? So but it actually went to actually minus 90 millivolt. So why it actually went? Because actually when it actually goes to minus 70 millivolt, so this actually potassium pump should actually close. So however, there was an actually delay in actually closing this actually potassium pump. So it actually went down to actually minus 90 millivolt. So then actually this actually potassium pump will be actually closing. So you can actually see over here. So this actually potassium pump, it actually closes, and then again what happens? So this actually mechanically gated maybe actually, or actually the sodium potassium pump actually comes into picture. So it actually gives 3 actually sodium actually ions inside and actually 2 potassium actually ions outside, and then it actually takes to an actually resting state actually potential. So this actually whole phase is actually called as your actually action potential. So when it's actually what happens actually, initially it was actually minus 70 millivolt. So what happens? So there will be actually a small actually diffusion of ions inside the cell. So it actually leads to actually minus 55 millivolt. So once it actually reaches minus 55 millivolt, this actually sodium actually ion channels get actually open. So more actually sodium ions actually come inside. That makes actually more positivity inside this actually ion or actually the cell. So that leads to actually plus 30 millivolt. So once it actually plus 30 millivolt is reached, the sodium actually ion channels actually get closed. The potassium ion channels get actually open. So more actually potassium will be actually going from inside to actually outside. That actually again reduces the potential inside the cell. So it actually comes to minus 90 millivolts. Then it actually the potassium ion channel actually get closed. So what happens? This actually sodium potassium pump actually opens in order to normalize, and it actually comes to actually in resting state potential. So this is your actually normal actually function. Whenever you want to actually act doing some function, maybe actually I'm actually thinking, I'm actually saying, or actually I'm actually hearing some actually songs, actually auditory, whatever may be, if there is actually a function has to be happen, so this actually action potential should actually happen. So now we have actually seen how actually the potential is actually crossing from actually your axon, from cell body through actually axon to actually this place, that is actually axon terminal. So now we need to actually see how is actually information from this one cell is actually transferred to actually another cell. So if you want to actually perform one function, not one actually cell actually should fire. There is an actual population of neurons should actually fire. So if there is actually a population of neurons should fire, one actually neuron should actually give information to the another neuron in order to actually perform an actual function. So you can actually see over here, so how actually a neuron actually communicate with an actual another neuron. So maybe actually some cases we need to actually stop the function. So when I am actually walking up to here, I need to walk and actually stop. So what that means is actually the neuron firing should actually stop. So it should not actually transfer the signal from actually one neuron. Or otherwise, if the neuron firing should actually continue. So that is actually called as an actually inhibition and actually exhibition. Either neuron firing should actually stop from actually transferring signal from actually one neuron to actually another neuron. That is actually the exhibition, or actually it should actually stop. That is called as an actually an inhibition actually characteristic. So this is actually done by another actually thing. I was actually saying one word, that is actually neurotransmitter. So this is actually done by this actually neurotransmitter. So that is actually made outside this actually cell body, and then it is actually transferred through this actually axon, and actually it will be available over here. So this neurotransmitter will be actually available over here. Once this actually action potential is happening, so that is actually your actually depolarization, that is actually going from minus 70 millivolt to plus 30 millivolt, and then it actually comes over to actually again to minus 90 millivolt and actually 70 millivolt. So this actually action happens. What happens is there will be also actually the calcium ion channels will be actually over there at the end of this actually axon terminal. So you can actually see over here the calcium channels are there. So this actually action potential is happening. So these calcium channels get actually opened. So that will be actually binding this actually fibers inside this actually axon terminal, and then it actually controls this actually neurotransmitter, and it actually pushes outside this neurotransmitter, outside this actually axon terminal. So there is actually a neurotransmitter is there, so it actually comes to this actually axon actually terminal. When the action potential is happening, this calcium ion channels actually open, so calcium ions actually comes inside, so that actually bind this actually fibers, and that helps to actually pushes out this actually neurotransmitter actually outside. So now where this actually inhibition happens and where this actually exhibition actually happens. So what this does is, so these actually neurotransmitters that may be actually binding with these actually ion channels and make them to actually open or actually close. So maybe actually it is actually opening, so it is actually pushing actually all these actually sodium ions actually inside. So what this actually action potential is actually happening. Or maybe, so this neurotransmitter can actually bind with these proteins actually available on the cell body or the cell wall, and can also actually open this actually ion channels. So what this actually sodium ions are actually coming inside, and then it actually makes actually the potential actually high. So action potential happens in the next actually neuron. So the one neuron neuron actually fired. So this actually neurotransmitter calcium ions actually channels open. Calcium ions actually came inside. So that actually pushes out this actually neurotransmitter. So the neurotransmitter actually bind with actually the ion actually channels in the next neuron. So that makes it actually opens this actually ion channels. So that actually in the next neurons actually ions actually comes inside. Then it is like the cycle actually continues. So either the inhibition or actually exhibition should actually happen over here. So what is actually inhibition? I said actually inhibition is actually stop firing, and the exhibition is actually to actually continue actually firing. So it can actually either open the sodium ion channel, so actually positive ions actually can come inside, and the neuron actually firing can happen because positive ions are actually coming inside, the positivity inside the cell actually increases, so it actually goes to actually plus actually 30 millivolt, and this actually neuron firing can actually happen. Or it can actually open this actually chlorine actually ion channels, so the negatively charged actually chlorine ions can actually come inside. So more negativity can actually happen, so that can actually inhibit this actually function, that is actually stop actually the neuron actually firing. So this is actually the whole idea of what happens when actually a neuron actually firing, and how an actually neuron is actually sharing the information from one neuron to actually another actually neuron. So this is actually happening in actually normal conditions. So in some part of the brain, there will be actually resting state potential will be happening. Maybe actually some part of the brain actually depolarization happening. Some part of the brain there will be actually hyperpolarization happening or actually repolarization happening. Maybe actually now my actually motor cortex is actually working because I am actually walking. And maybe actually my actually auditory maybe actually may not be actually functioning well because actually I don't want to actually listen others. So I'm just actually talking. So maybe actually it will be in the resting state. Maybe may actually motor actually maybe actually activating. So different actually regions will be on actually different actually potentials on the surface of this actually your brain. If you keep some actually electrodes on the surface of your actually brain or actually on the surface of your actually scalp, you can actually acquire this actually potential. So that is actually recorded as an actually EEG actually signal. So you can actually keep this actually different actually electrodes on the surface of the scalp, and you can actually record this potential. There are actually different actually criteria are there, 10 to the electrode system. You need to actually measure how you can actually fix the electrode. You can't randomly, you can't actually fix the electrode. You need to measure the distance from here to here, and then after 10% of the total distance, the first electrode you need to keep, then actually 20% of the distance you need to keep the next electrode. So there are actually different actually criteria are there, 10 to the electrode system, 10 electrode system. So that I am actually not going to actually unipolar, bipolar actually that I am not going to actually explain over here. So what I am actually interested to actually explain over here. So in the case of actually normal actually brain, so these actually neurons actually either fire in the controlled manner, and they may be actually communicating, they may be inhibiting, they may be actually exhibiting. Some cases in the abnormal conditions, so these actually neurons may be actually firing in an uncontrolled manner. So such kind of uncontrolled neuron firing, one of the condition is called as an actually seizure, and an actually a multiple actually seizure is actually happening in a subject. So that disease condition is called as an actually epilepsy. So you can actually see over here. So in the case of normal condition, in me actually, I hope it is actually neuron is actually firing in an actually controlled manner. So what I am actually walking in a controlled manner, I am actually speaking in a controlled manner, I can actually grasp everything, so it is actually going fine. So however, in the case of actually some actually subject, this actually neuron firing may be happening in an actually abnormal actually manner. So that is called as an actually seizure. If there is actually multiple seizure is actually occurring in a subject, the disease condition is called as an actually epilepsy. So such kind of actually subject may be causes triggers actually, maybe because of actually trigger or actually injury, because of actually tumor it can actually cause, and actually it leads to actually loss of actually muscle control and actually convulsions. And there is actually who says that around actually 50 million actually people are actually affected by actually epilepsy, and it is actually the second most actually commonly occurring neurological disorder. And in India it is actually around 12 million actually people are actually affected by actually seizure. So how you can actually diagnose this actually seizure? So which part of the brain the seizure is actually occurred? So there will be actually different types of actually seizures are there. If you actually find an actually type of seizure, you can actually apply a particular actually medication. And also when the seizure will be actually occurring. So if you can actually predict in the next actually 5 minutes or actually 2 minutes, the seizure is going to actually occur. you can give an actually proper medication to the subject and actually avoid the seizure to actually happen. So this can be actually done either by an actually EEG signal, maybe an actually an MRI, maybe an actually CT or MEG. There will be actually different actually modalities that there. So one of the simple modalities that can be actually used to actually predict the seizure or classify the seizure or whether the seizure is actually happened or not. Maybe actually mild seizure may be actually happening in the physiologically, it may not be actually visible in the behaviorally, but you can also actually diagnose through an actual imaging or actually signal processing, signal modality. So one of the modalities actually EEG. So you can actually see over here there is actually an, we are saying like this is an actually an EEG signal. So there are actually four actually different actually parts are there. So one is actually an ictal. So there is actually a seizure duration. So the duration of actually the seizure we are actually calling as an actually an ictal. So duration after the seizure that is called as an actually an post-ictal. And actually the duration before this actually seizure is called as pre-ictal. And the duration between two actually seizure is actually called as an actually an inter-ictal actually period. So we are actually interested to know if there is actually a difference between this actually ictal period, that is actually a seizure duration, and then before the seizure is actually going to happen. That is actually you can call it as actually background or an actually pre-ictal actually period. So if there is actually a difference is actually you can actually see from actually a background, then actually there is a pre-ictal period is actually there and the ictal period is there. So before occurring of the seizure, whether you can actually predict that the seizure is going to happen or not. So before this actually heart attack is actually happening. So if you have an actually pacemaker, actually very good pacemaker, it can nowadays actually detect so whether this heart attack is going to happen. Similarly, before actually the seizure is going to happen, or actually maybe 5 minutes before, actually 2 minutes before, actually 7 minutes before, whether we can actually predict this actually seizure, so that you can actually indicate maybe to the subject, you can actually make a wearable or an actual mobile, and then it can actually give a notification that in another 2 minutes or actually 3 minutes the seizure is going to happen. You can take an actual medication so that you can actually get in an actual normal life. So that is our actually research actually question. So it can actually prediction using EEG can provide significant insight regarding actually epilepsy, avoid triggering, improve the quality of the life, and prepare actually a suitable medication. So further we had actually some objectives. So we need to collect the EEG signals and then to actually pre-process the signals. The signal will be having actually a lot of actually noise. So we need to remove this noise and then we need to actually extract the features from these actually signals. So initially you can't actually see there is actually a seizure is happening or actually background. So you need to actually compute some features from this actually signal and then you need to build an actually machine learning model in order to predict this actually seizure. So here is our actually small process pipeline. So for our actually analysis, we have actually collected data from actually QH, so that is actually one of the largest actually seizure or epileptic database, EEG database. Also we have actually collected some data from Sri Chitra and also from actually Minhan. So but for this study we have actually used only the data from actually QH, and then maybe actually different subject may be there. So for few subjects maybe actually one channel maybe data may not be recorded, or maybe the electrode may be off, so data may not be there. So maybe 32 channels they have actually recorded, maybe actually 18 channel information will be there. So we have actually selected only the common channels that has all the subjects actually has this actually channel information. So that channel only we have actually considered for the analysis. And then we have actually conventional pre-processing algorithms we have done. So notch filter in order to actually remove the power line actually interferences, and then actually high pass filter to cut actually the frequency of actually 1 Hz we have used, and we have actually downsampled to actually 250 Hz for actually better process. So then we have actually segmented this actually signal to an actually 20 seconds. So the seizure is actually 20 seconds. So before the seizure 20 seconds, with actually 10 second actually overlap we have actually cut. So we'll be having actually basically then actually seizure signal of actually around actually 20 seconds, and before the seizure there will be actually 20 seconds, like this we will be going. So this is actually just before the 20-second seizure, then before, like this we will be actually going. So we will be seeing that how many actually seconds before we can actually predict the seizure. Basically it will be a classification problem. So we will be seeing that what will be the difference between this actually seizure segment and the before the seizure segment. How much actually the difference is actually over there. So then we'll be actually computing these actually features, time domain features, frequency domain features, time frequency domain features, and then we'll be actually building an actually classification model in order to actually predict whether the seizure is going to happen or actually not. So as I said, we have actually considered data from this actually TUH data set. So it consists of around 579 epileptic patients. And each file is actually annotated what is the duration of the seizure and what is the background duration that is actually well actually annotated. So in our actually study, we have considered if this actually minimum of actually 1200 seconds of the signal is before seizure onset is there, then that signal only actually considered, because actually we are actually going actually every 20 seconds actually over here. So at least actually this duration is actually around 1200 seconds. So that actually segment only we have actually considered in our study, and minimum size of this actually seizure duration is actually should be 20 seconds, and the number of there will be actually around actually 579 epileptic patients here there. So based upon our actually inclusion criteria, so we actually end up with actually around only actually 50 subjects, and actually the number of seizures actually considered over here is actually 87 actually seizures. That means actually 89 seizures segments, and then actually its corresponding actually background or actually the pre-ictal period also we are actually considered. So these are actually the statistical actually or actually the time frequency domain and time frequency domain features. So there are actually simple features like energy, entropy, absolute energy, absolute entropy, and frequency domain features. We have actually decomposed into different frequency bands, and also we have actually used that for actually time frequency in order to actually compute these actually features from the signal. So this is actually little surprising, like the graph is actually x-axis is the time, that is actually first 20 seconds when we used, next 20 seconds we used, and that is next 20 seconds. So it actually goes up to actually around actually 60 seconds into 20. So what it is actually 1200 actually seconds. So the earlier slide I have actually explained. Only this actually pre-ictal period that is having 1200 seconds is actually we have actually considered for analysis, and y-axis is where actually accuracy, that is actually the classification actually performance. So you can actually those who know the machine learning algorithm, they can actually say like so when it is actually near to this actually seizure, just before the seizure, the accuracy is actually fine, and when actually going actually little actually backward, so this actually accuracy actually reduces. So however, the best accuracy is actually achieved is only around actually 60%, around actually how much actually second we have actually achieved. Sorry, it is not actually much visible. Yeah, around actually 0.6 minutes, that is actually around actually 280 seconds before. So we have actually achieved around actually 60% of actually accuracy. So last actually 3 years we are actually working on it. So now just we have actually, this is actually around 6 to 7 months before result. So we have actually used different techniques, we have actually used different algorithms, we have actually used different data sets, even Indian data sets. So we are actually able to achieve around 66 actually percentage of accuracy. So you can actually see over here in this actually seizure research, there may be actually different studies that have been actually used seizure type classification, seizure detection. However, there will be actually minimum studies will be there in actually seizure prediction. So that is actually one of these actually hot research in the epilepsy. So there won't be actually any standard software will be there to actually predict the seizures. So however, we may take it as a challenge. We know that in terms of publication, in terms of actually taking the results, we won't be having actually materialize, or actually we will be, there is actually unpredictability will be there. So if you want to actually publish, if there is actually very good known problem is there, well established literature is there, you can actually do something and you can actually publish well. So however, in this case we know that we may not be end up with something, but we taken it as a challenge, and we actually worked around last 3 years. We achieved around 66, 60 to 66 we actually moved. So hopefully we are actually trying to build some software for patenting and actually selling this actually as a product. So based upon our actually classification, so for few subjects we are able to actually achieve 100% also. So for few subjects, we are all the seizures we are able to actually predict. That is, you can actually see around 100% also we achieved. But few subjects we were not able to actually predict. So it actually, the total average accuracy was actually down to actually around 60.76 and around actually 2 to 80 seconds before we were actually able to actually predict. So a few limitations we have actually matched up now. Actually in this study we have used only actually XGBoost. So we are trying to use other classification algorithm and deep learning algorithms. So in this actually you can actually see very simple time frequency and actually frequency domain features we are actually computed. And we are actually improving the complex and we are trying to implement complex algorithms. And this is actually only one site data we have actually used. So we are actually collecting data from other sites also, and we are actually trying to implement the implement. And only 20 minutes before we have actually considered, that is actually 1200 seconds we have actually considered, that also we are trying to actually increase in order to actually optimize the results. So there is actually few limitations in the case of EEG. So if you want to actually there is advantage also. So I said, like, if you want to continuously actually monitor, EEG is the best actually device. And but there is actually limitation is there. It can be actually placed on the surface of the scalp only. There is intracranial EEG is also there. You need to actually operate and you need to actually fix inside this actually scalp. But however, there is actually high possibility of infection in the day-to-day activity. You can't actually monitor. So we should be actually in the clinical environment. So there are actually videos I am also seeing, like they are actually doing intracranial and trying to actually do day-to-day activities, but I don't know how much it will be feasible. Sweating will be there, so it can actually add the infection. If there is actually other water inflammation will be actually there. So if the seizure is actually on the surface of the skull, you can actually predict because you are keeping these electrodes on the surface of the skull. Or if the seizure is actually small and if you are actually keeping the electrodes actually very distant, it may not be able to actually pick the signal. Right? So, or the seizure actually should be actually very much actually higher, the seizure region should be higher or the potential should be actually higher. Or if you actually keep this actually, if the seizure is actually happening in the deep inside the brain, so the potential actually you may not be able to actually measure. So here the seizure is actually very small and you may not be able to actually measure. And the seizure is actually, you can't expect that always actually seizure is actually happening on the surface of the brain, deep inside the brain also it can actually happen. So your electrodes may not be able to pick the signal. So these may be actually the limitations. However, if you go for an actually an MRI also you can't actually occur actually periodically, right? You don't know when the seizure is going to happen. So immediately you can't actually take the subject to MRI machine and acquire the data. So there will be actually limitation in the MRI also and also in the case of EEG also. So however you can actually choose it according to your actually research. So we have more time. Okay. So I want to actually also discuss about actually MRI. So that is my actually core area. So we are actually working for last actually 15 years. So he is actually an adopted child. So when I joined over here in Varanasi, so it was COVID time, so we don't have access to actually highly computational actually machines are there. So I thought of actually doing actually downgrading to actually one-dimensional actually signal. So what I actually started working in actually EEG studies. So how actually an MRI actually signal is actually accurate, that I am going to discuss in the next slide. So we have actually our friend protons. So these protons will be actually in fat, muscle, sugar, water. So all these are actually in our actually body. So So I'm skipping this actually. I'm interested to actually discuss this one actually, rather than research. Yeah, one simple study I will actually explain here. So I'm more interested to actually work on autism spectrum disorder. So that is actually one of the neurodevelopmental disorder, basically in the newborn babies. So this kind of actually disorder happens. So this disorder is actually because of the abnormal growth of the brain regions, maybe actually overgrowth or actually undergrowth of the brain regions. So in the case of actually normal subjects, this actually there will be a normal growth of the brain. So there will be actually everything will be learning, will be actually communicating. In the first slide I have actually explained like how actually neurons will be communicating and how the neurons will be actually firing. So this all actually happens in actually a controlled manner, and then actually development will be actually gradually actually good. So however in the case of autism actually spectrum disorder, so this actually development may be actually arrested. So what they may not be able to actually communicate well. So if you actually call them actually, they will be actually the sound will be going to actually maybe actually auditory. There may be actually going to actually an auditory cortex. In order to actually process this actually signal, so it takes actually some time because actually the neurons are actually not able to actually fire, or the neurotransmitters are actually not actually generated in order to actually process or actually activate this actually exhibition of this actually neuron. So autism is an actually spectrum of disorders. So that is actually an autism disorder, pervasive developmental disorder, childhood disintegrated disorder, Asperger syndrome. So these are actually now collectively called as an actually autism actually spectrum actually disorder. So there is actually challenges in actually diagnosing autism spectrum disorder also. There will be actually usually clinicians will be diagnosing autism based upon your actually behavioral actually symptoms, maybe actually learning problems, intelligent quotients. They will be putting lot of actually questionnaires, and based upon these actually questionnaires they will be actually answering. So based upon that maybe actually verbal questionnaires they will be asking, or maybe non-verbal questionnaires they will be asking. So based upon that they will be actually diagnosing actually an autism spectrum disorder. However, these may be actually subjective. So maybe actually people from actually one territory may be actually behaving something different. Another territory may be actually behaving actually something different. So you may not be able to actually predict or actually diagnose autism spectrum disorder actually well. Or maybe the regions affected. For actually some actually subject may be actually corpus callosum may be actually affected. For some subject maybe cerebellum may be actually affected. Some subject may be actually brainstem may be actually affected. So it is not actually constant. It may be actually vary with respect to actually the subject. So if you can actually image the brain of this actually subject, and if you do some actually image processing and actually machine learning or actually pattern recognition, you can identify that which part of the brain is actually affected in a particular actually subject, or which part of the brain is not able to actually perform its actually task in a particular subject. You can actually apply particular medication, or you can actually train them, or you can actually apply particular actually therapeutic to actually the subject, and you can actually recover this actually to an actually normal actually condition. So for that we are actually using the imaging modalities. We are actually using structural imaging, functional imaging, and actually DT actually imaging modalities. So one of the study we have actually conducted is, so we have actually taken this actually MRI image of this actually subject. So conventionally what they actually people do is, so they will be actually extracting these actually features from this actually MRI. So you can actually see over here the structural MRI images. So they have actually skull stripped the images or the pre-processed the images. There will be actually a conventional actually pre-processing step is there, reconstruction, registration, all this they would have done. So then they would have actually segmented the brain regions. So you need not actually analyze this actually whole region. You can actually segment the brain into actually different regions, and then you can actually analyze this actually brain regions. So traditionally, how the segmentation is done? So there will be actually level set algorithms, there will be actually thresholding algorithm, there may be actually clustering algorithm will be there. So there may be actually based upon the intensity difference in the images, may be actually segmenting these actually brain region. So however, these kind of actually techniques may not be able to segment all the regions. So this may be actually working based upon the boundary edges or maybe actually intensity in the images. So that may not be able to actually segment all these actually regions actually well. So what they are actually doing is atlas based actually segmentation they are actually doing. That means actually the scientists or actually researchers actually predefined the brain actually regions, and they will be having this atlas, and they will be actually mapping this atlas with your actually image. So automatically it will be actually segmenting this actually brain regions. So here also there will be actually disadvantages will be there. So your actually brain map maybe from actually 24 years old, and if your actually image is actually acquired from an actually 6 years old, so it may not be actually matching, and there is a possibility of actually over segmentation or actually under segmentation may be actually occurring. So however, so you need to actually choose an actually an atlas that is actually with respect to age and territory. You need to actually choose an actually an optimal atlas, and then you need to actually segment this actually brain region. And there will be actually different actually features you can actually compute from this actually brain region. Either you can compute the volume of this actually brain, you can actually compute the surface area of the brain, you can actually compute the thickness of the brain. So all these features will be actually traditionally actually computed, and then they will be actually given to machine learning models in order to actually construct this actually diagnostic classification model. So what we have actually done is we have actually made an actually morphological distance actually related features, that is actually feature computed from actually one region. We have actually compared it with actually another region, and then we made an actually feature matrix. So that feature matrix we have actually given to the machine learning model. So what is our actually result says this actually, when we are actually building an actually model with an actually a normal actually features, that is actually we have just actually computing this actually volume or surface area or maybe thickness or verification index, and then we are actually giving to the actually machine learning models. So here we have used RF, SVM and MLP. So we achieved an actually classification accuracy of around actually 69 actually percentage. So however, when we are actually using actually our proposed approach, that is actually we have actually computed this actually morphological distance related features, the accuracy actually jumped into 82.91%. So the hypothesis here is like we are comparing this actually one region actually maybe overgrowth, maybe another region is actually an undergrowth. So that we are actually comparing by using this morphological distance related features. So that may be actually help to actually improve this actually classification accuracy. So we have actually seen that which actually region of the brain is actually highly affected. So it is actually varying with respect to our actually study. So in the one case it was actually parietal, there is only morphological features. So however in the case of actually morphological distance related features, around 30% of the significant features is actually from the frontal lobe. That means actually the frontal lobe there is actually huge differences between the autism and actually the normal kids. Okay. So I'm winding up here. Any questions? Yeah.
So for the morphological distance formula, basically it works by finding out the average deviation of the points between two images. So I'm wondering, how do you reduce the error if it's like different images from various different equipment?
The distance is we are not calculating between the subjects, but within a subject, different regions. So maybe corpus callosum, brainstem, cerebellum, thalamus, hippocampus, frontal lobe, parietal lobe. So we are actually computing, and from there we are actually taking the difference. So to ensure intra-subject actually variability, so we are actually ensuring that when we are doing this actually pre-processing itself, so all the brain regions are actually available or not. So when you are actually sometimes doing registration or maybe actually this skull stripping, some part of the brain will be actually chopped out. So that we will be actually concatenating with all the images, and at least actually 95% of the subject actually data is actually there. Then only we are actually considering that actually subject. The other subject we are actually exploring. So similarly for actually brain region segmentation also, we are ensuring that at least 80% of the subject has this actually region. So then only we are actually considering that actually subject. Otherwise there won't be actually meaning in actually the analysis.
Those two studies, I've been second study at least. First one is very interesting. I'm just curious. So when you were talking about the efficiency, you reached around 66%. So what's your plan? Because 66 is a good number because this is something that you say you have not been able to compare with previous studies and all the prediction part. So how do you think you can increase this to a good number so that it can be used by all neurologists?
There are two options are there. One is this itself it is difficult to actually hear this actually EEG. Our whole idea was to correlate this with our actually ECG signal, and then we can actually make it as an actually wearable. So however in the EEG itself we are actually struggling with actually 66%. But what we actually seen is from actually 60%, initially we are actually struggling with 55%, that maybe machine learning algorithm may be actually giving 50% chance so that you can't actually construct. So 55 to we reached to 60 and 62 we reached to 66. So hopefully we are actually trying to use now actually deep learning algorithm. So maybe we will be actually reaching to maybe 70 to 75%. So that may be actually a good number, not actually all the time it may not be actually working, maybe actually there will be false detection also, false alarm also. But actually if we are able to actually reach 75, then we will be actually happy to actually do that. But sir may not be actually agreeing that. But and as business point of view, to pitch it, maybe actually I'm feeling. We are actually discussing about different things yesterday. So I was saying like 99% accuracy is actually required. So we don't know. Yeah. But I think if we are actually succeeding, I think we will become a billionaire. But another problem is I think source localization, that is actually another hot topic. Thank you. Thanks to my senior Nathan, we were closely associated with. Happy to see him here.
So, thank you, sir, for sharing your insights on neuroimaging and computational neuroscience. Your perspective has opened new avenues for inquiry and innovation, and we appreciate your valuable contributions today. Thank you, sir. As a token of our appreciation, we could now like to facilitate our esteemed speaker, Dr. Jack Ferredo. I kindly invite Professor Fong Xing Yu to come to present a memento to Dr. Jack Ferredo.
Background, please.
Oh, big wow.
Yeah, thank you, sir. Thank you, Professor Fong Xing Yu, for doing the honors. Thank you all. And it is an absolute privilege to welcome a distinguished innovator and leader in the biomedical engineering, Mr. Sharath S. Nair, with an MTech in electrical engineering from NIT Calicut, where he was a first-rank gold medalist. He has made remarkable contributions to medical device development, artificial organs, and AI-driven healthcare solutions. Currently serving as engineer at Sri Chitra Tirunal Institute of Medical Sciences and Technology, Government of India, Mr. Sharath has played a pivotal role in developing and commercializing cutting-edge medical devices in collaboration with leading industry partners. His research in total artificial heart, ventricular assist devices, AI-driven anesthesia systems, and targeted drug delivery has set new benchmarks in biomedical innovations. His work has also earned him numerous prestigious awards, including the DST, SCRB, NIAE, APJ Abdul Kalam National Technology Innovation Fellowship 2023. With such an extensive expertise and groundbreaking contribution, we are truly honored to have him here today. Without further ado, let's extend a warm welcome to Mr. Sharath S. Nair as he takes the stage to enlighten us with his insight. So the stage is yours. Sir. Thank you.
Very good morning to everyone. And, thank you for the nice introduction. I thank SSN University for having me here today to discuss about one of the most complicated medical device ever attempted by mankind. The device is none other than an equivalent of one of the most complex natural organ, the heart. Now we'll be talking about creation of artificial heart, the current status of its development in our country, where we have reached globally, what is the technological advancement required henceforth by the people gathered here. We can also work on, inspired by the challenges which I am posing, work on something new so that will finally add on to make this into a reality. This is a photograph of my institute in Kerala, Trivandrum. It's an institute of national importance in the government of India, and our primary responsibility is to make medical devices for the country. Moving on, if you consider the recent report on what are the world's leading causes of death, you can easily find from the numbers that the heart diseases is a major cause of death all across the world. Then comes the neuro problems that my colleague Dr. Fredo is working on. We have got many other diseases which needs attention. But if you consider the numbers, the quantitative figures, we have to prioritize the actions that we have to put on finding out a solution for creating developments or creating innovative methods on identifying, solving, and then deploying it in various hospitals across the world to make it useful for this fellow patients. So what are those problems? These problems can be a heart attack, which you know, a myocardial infarction, we used to say clinically. There can be a sudden cardiac arrest. But moving forward, some of those things which you don't know, we call it as heart failure. There is a very big difference between a cardiac arrest, which most of us know, and the heart failure, which none of us have seen or not known about. So this heart failure is a kind of a disease where the aging, the weakness of the heart propagates and progresses for a long time, and finally the heart comes to a stop. Then we call a death, or a complete stopping of the heart leads to immediate attention requirement in a hospital. But since we don't have a treatment option, it may not be possible to do immediately. In India, as of now, we have more than 1 crore of people having an immediate attention, seeking immediate attention, but we could not do anything to them. The prevalence is very high in urban areas, and half of that is the prevalence in rural areas. So if you see these diseases, we can classify these diseases into 2 types. One is a circulatory related disease, and another one is an electrical related disease. It's any research on biomedical is actually a combination of many areas. You have physics playing into it, you have electronics, you have electrical, you have chemistry, you have biology. It's a mix of many things. So the understanding also should be a mix of many things. So if you want to work on it, you have to understand where exactly the root cause is. In this particular case, you have got a heart beating, and there can be multiple problems to the heart. It manifests as different symptoms. But what is actually inside happening within the heart, it may be some problem related to the circulation of the heart muscles, which is happening in the heart muscle. You know, heart is the organ which pumps the blood, but for heart to function, it also needs blood. It also needs oxygen. So it is something like the primary function of the heart itself. For that to function, it also needs the same output. So it's kind of a positive loop. So if some problem happens to that particular loop, then an issue happens to the heart's output, right? So this circulatory problem can be of different types that we know. I will take the first one which you know. It's a myocardial infarction, or seems to be like a heart attack. There are solutions for that right now. It is now available not only in super specialty hospital, which was there 40 years back. Now it is there in every, in any corner you go, there may be a hospital, and the hospital you may be able to find an angiogram, a diagnosis for identify a block is there in your heart, and then they do a corrective measurement. So the research which was done 30 years back by the universities all across the world have now come up with solutions which are possible in hospitals. So they really could deploy a mechanical device called stents, which are put there. You can see the picture. So this is a stent developed in our institute. It's there. It can help a patient come back from this heart attack problem, so myocardial infarction. So what next can be the problem? The next problem can be a valvular problem. You know, this heart has got 4 valves. It has got 4 chambers. So all these chambers are separated by 4 valves. So these valves can have problems congenital from your birth, or it can be an acquired because of your sedentary lifestyle, or it may be something which is beyond your control. You call this like calcification, your aging related problems. Or it may not be because of you. It might have happened because of your some problems within your body, your make of your body. So this calcification and all may lead to problems of the valve. Now we can see the opening and closing of the natural valves happening there. And if that didn't happen properly, then we need to have mechanical valves. So these valves control the flow of heart between the chambers. 1979 we started the work on developing a valve, and by 1990 we did the first clinical trial. More than 35 years now we have the valves available for Indian population made by our institute. Now more than 2.5 lakhs people in the world and especially in our country are living with this mechanical valves which are made in our country. We should be proud that these valves are helping the fellow Indian citizens. Otherwise they would have not been there in the world, or they would have denied the medical treatment because of the exorbitant cost of the devices coming from the West. So what are the next issue? This you may not be knowing, but if I tell you the issue, then you may be understanding it. We sometimes find that babies are born with holes in their heart. So such kind of problems in a clinical terminology we call the septal defects. So what is a septum? The septum is that region you can find the separation between this wall is called septum. So when this heart is naturally grown within the womb of a mother, the septum starts moving from both directions, and then it finally comes to a junction. So this junction, if it is not closing properly, there can be a hole. Maybe your grandma was maybe telling to your mother or to your caretakers when you are born that the baby has to cry. The first, the spontaneous reaction of a baby should be crying. So the crying is a spontaneous reaction, but it naturally occurs to create the septum to close. If it is not closing, there will be a small gap in between, and that creates a mixing of blood from the non-oxygenated region to the oxygenated region, and that reduces the efficiency of the heart output. So this has been naturally happening for almost everyone born on the world, but to a few unlucky people, there may be a small hole in their heart. But now there are medical treatments to correct that, and that is shown there. It's called ASD closure device, atrial septal defect closure device. This is made up of a particular type of material called nitinol, nickel titanium alloy. It's a special alloy made with nickel and titanium which can memorize its shape. So that's one of the beauty of mechanical engineering nowadays, that now you can program in a microcontroller the same way you can program a mechanical structure. The mechanics of the material changes by programming it, and the programming language is temperature. So you can create different temperature profile, and you can create a structure, and the structure it memorizes the structural shape which you have programmed, and it can be deployed in a human body for helping a patient like this. So there are other defects. The defects may be the output of the heart. The heart is connected to a network of nearly 50 million kilometers of blood vessels in your body. So if any of this blood vessel has got some issue, we call it as aneurysm. This aneurysm is a bulging of a blood vessel, and it may break at any point of time. You may not be knowing the breakage, and it oozes out the blood from the body, and if it is on a large blood vessel, you need immediate attention. And for that, we have created an artificial blood vessel. This is an artificial blood vessel. It can be put on a human body in a surgical method or in a minimally invasive method. When you come into the electrical, it may be there in your syllabus. You may be knowing about all these things of electrical problems. The electrical problems are basically fibrillation or the non-synchronized movements of the muscles. But really, where is this problem happening? The source of this problem is on the electrical pathway. You could see this light flashing. The light starts from the SA node and then passes into the AV node, and then it branches into different portions of the muscles of the heart, and then triggers. The same thing what my good friend has talked in the first talk about the neurons of the brain. The same type of conduction happens in the heart in an independent way. And if that conduction has got some problem, just like the seizures happen for the brain, there could be seizures of the heart. So this seizures is we call fibrillation and flutter, which leads to cardiac arrest. So now there is a solution for that. The solution is called the defibrillator. You might have seen defibrillators in airports or railway stations or in big malls and all. You can have that defibrillators of the size of a suitcase miniaturized into a small device like 2 or 3 coins stacked together and kept in your body. So that device is an advanced version of a pacemaker which can help you to come out of this situation. It has got predictive tools also. It will find out where the fibrillation happens, at what time the fibrillation can happen, and prevent you from having that. But moving on, are these the only issues of the heart? Most of these issues which I said are being able to correct now, but there are certain issues which was not attended at the right time, but it progressed. It keep on progressing. Heart is an organ, just like any other organ of the body. It should have needed some rest, but we cannot do that. No, it's an involuntary thing. You cannot voluntarily keep heart in rest. When you are sleeping, that time also the heart is actually working. Maybe your brain would have shut down for a few minutes or in the deep sleep, but your heart is never in rest. So heart is continuously pumping. And what is in terms of numbers? In an average lifetime of nearly 60 years, if you take, the heart, a healthy heart pumps for nearly 2,500 crore times. No mechanical, no electrical, no electronic, no engineered products have that much of reliability. So 2,500 crore times without change in its efficiency. That's the biggest point. Now, you can make something work lifelong. Maybe an engineering device can work for lifetime, but it has to do in the same fashion it has worked for the first day, till the last day. That's what we say efficiency. So what is efficiency in terms of the requirements of heart? The efficiency we call like flow rate and the pressure, the blood pressure and the cardiac output. The cardiac output is usually for a person, a healthy person. If your weight, if you know the weight, you can find out what is your cardiac output. If your weight is 75, you just multiply with 70. So you will have approximately 4,900 milliliters per minute. That is your flow rate. It comes to around 4.9 liter per minute. So this cardiac output, depending upon your weight, it has to be there. When your weight increases, naturally there will be a decrease in that cardiac output, but your heart has to work more to overcome that problem. Now, what should be the pressure? The pressure should be in between 100, average of 100, between 80 to 120 mm of Hg. That is the pressure requirement. But let's suppose, as shown in this particular video, now the heart is kind of weakened. It is slowly, it slows down, and if it stops, because heart is also an organ, it can age, it is aging, it can also have fatigue, See, in some case, a natural heart which is beating at 72 beats per minute, it finally have reached into a point that it could not do the same thing again. Then it slows down and then it stops. So this condition is called end-stage heart failure. Okay, it's different from heart attack. Heart attack is primarily due to a problem with the blood, a problem with oxygen, or a problem with the electrical system. But it is a problem with the heart in total. So what we can do to correct this? What we can do to get rid of, or to at least help those patients to live for some more time? If the patient is an young patient, we need to give him some more time. So we would like to extend the life of such persons. So in what way we can do that? So let's see the therapies which are currently available all across the world. One of the best therapies is just medical. You start with pharmacological intervention. You give medicines, but none of the medicines have really created a solution to it, but it could improve the symptom. That means it reduce the pain, it could give more time. But finally, it will never solve the problem. Okay. Then what is the next thing what we can do is a surgical correction. What was the underlying problem which created this issue? Is it a valve problem? Is it a bloodstreams problem? You try to identify it with some diagnostic techniques, and as much as early as possible, do the surgical correction. Right? If the surgical correction can be done, then it will help the patient to come back into normal life. So what are the surgical corrections which are possible? Angioplasty, open heart surgery, valve repair, all those things are the surgical corrections. So this surgical corrections will try to relieve symptoms, but may not avoid the progression. If the root cause is something different, it will not avoid the progression of the disease. So the best possibility would be a replacement. Okay? Replacement is what? You get a donor heart from somewhere, you replace it on the patient. Okay? So this donor heart, if you want it, you cannot get it on time, right? You know the problems of it. And the worldwide, the number of donor hearts are also very, very limited. You cannot get the donor hearts, like off-the-shelf donor hearts are not available. You cannot get it from a store or a medical store or from a clinical store. You cannot get a donor heart. You should have a donor who is like nearing to death or has a brain death, and then get that donor heart after consent, transport it into the region where this surgery is going to happen, where the recipient is available, and then take it. Unfortunately, the best of the transportation and the policies and the other mechanisms which we can rely upon, we could not have the heart available on time, which is less than 4 hours or 5 hours, because we call this as the viability time. An organ has got some viability. If you take an organ, we take fish. How much of time the fish will be kept fresh? You take any meat, you cannot keep it for a long time. If you are even keeping in a refrigerator, you are not happy with that. You may not be able to use it after a few hours or a few days. You will not keep it fresh. So that is not the problem. So it's not fish or meat now I'm telling. I'm telling about what? An organ. Okay, we are not interested only about the protein. We are interested about the life of it. Right? So this organ could not be used after 4 hours. This 4 hours is called the viability of the organ. If you want to have that same organ used for an 8 hours time or a 10 hours time, you need to expand the life expectancy and then expand the viability of that particular organ, which is altogether a different research, which has not been really created by anyone. There are attempts. That is called organ care and transport mechanism. Organ care and transport mechanism tries to improve the viability of the organ, extend the life of the organ after the donor, it is taken out from the donor, till it reaches to the recipient. If you could expand the viability of an organ to 24 hours, you can bring it from America. Now it's not possible because you can only take from a place which is 4 hours away from you. Right? So that is the current situation. So what is the next possibility? From an engineer, I am an engineer. From an engineer point of view, I would only think about something electromechanical or mechanical or electronics related. So that is called a substitution. Can we substitute the function of the heart or in total the heart with some mechanism? So if we can substitute that, then we call it as an artificial heart. The substitution can be the entire heart or a part of heart. The function of the heart has to be substituted. We are interested in that. We are not interested in the morphological similarity, but we are interested in the functional equivalence. Okay. So what is this artificial heart? whether have we done that? Do we have a artificial heart in place? Can we buy an artificial heart and use it on a patient who is dying? The first attempt of making an artificial heart was along with the moon mission by NASA. It was done by Texas Heart Institute in America. And the first patient was Domingo Loyola, and he was the team leader, and it was put on a recipient called Haskell Karp, and he lived for just 64 hours. So, but that was history, that was medical history. He could live for nearly 2.5 days. So this has started the research on medical devices, in fact, in 1969. After that, there were a lot of inventions, the pacemaker and all actually started developing after this invention. But this invention got little progress later. After 20 years, they have matured into this stage, and now we call it as total artificial heart. So what it does, it is basically replacing the chambers of the heart with mechanical chambers, and the mechanical chambers are operated pneumatically or hydraulically or electrically with some kind of power sources kept outside with a huge pack of systems. It would be like an Iron Man holding all the electronic stuffs, and then the person lives. How much time? That was the concern. Increasing the reliability of the device to make the person live. That is what we call survival rate and the survival time. The survival rate was so less during that time, it was like less than 30%. That means there is 30% chance that the person survive for the first day, first hour. And then what we have increased the research funding all across the world. People started working on providing any technology which is currently available on the ground to put in this technology, and by 2020 this heart is now available, total artificial heart. This is an Australian made heart, and 2 weeks back the first clinical trial, the first patient who got this heart lived for 100 days. Yeah, it's for 100 days, and the 100th day he got a donor heart. That means what I said in the beginning is like a person is dying and you need another person who is going to die but brain dead, has to get the heart from him within 4 hours. Now with the technology, we have now an option of increasing the life expectancy of the dying person to now 100 days. So within 100 days only you need to find out a heart. With some logistical mechanisms, you have to get the heart. But this is enough? I say no, it is not enough. Not all researchers working in this field will find it appreciating. But this is a very big beginning. This took nearly 70 years. From the first 62 hours, 64 hours to 100 days, took nearly 70 years of development. So why so much of time taken for development? Why is it happening? If you look into this artificial heart, the approaches for the artificial heart, this is the quite common thing what I have mentioned. Replace it morphologically. You take out the living heart and then put an artificial heart. So that was the way the approach was. But this approach needs a correction. Do we really need the complete replacement of the heart? Do we need to really cut off the entire natural heart from the body and then put a mechanical heart? So what it has been found out earlier was it is not really required. See, we will have another picture, it may be there from your textbook. There are two circulation loops which are working parallel in your body. There are two loops. One loop is called pulmonary circuit and another loop is called systemic circuit. The pulmonary circuit is the blood going into the lungs, get oxygenated, return back to the left side of the heart. It comes to the left atrium. Then from the left ventricle, your real heart pushes the natural heart pushes the blood into all across your body. That flow we call systemic circuit, right? So the pulmonary circuit, it's more or less constant for everyone because the lungs are fully expanded and the oxygenation requirement is almost constant, and if that does not change. So only the average values maybe have a slight 1%, 2% variation from one person to another person. But whereas the systemic circuit, it is not like that. Your height, your body mass index, your weight, your total surface area, everything is a factor which determines the systemic circuit requirement. If you are more physiologically dynamic, you need more flow and more, and more flow, the pressure remains the same. So this is a requirement of the systemic circuit. So that means out of the 4 chambers, the collection of 2 chambers left side really works more than the right side. If you understand that, then we can give a solution. Why do you want to completely cut off the heart from your body? You just want to assist the left side. You need to put one small pump within the body, which is in connection with the left ventricle, get the blood from the left ventricle, push it into where it was naturally giving. It is naturally giving to where? Aorta. So if you can bypass the natural flow from the left ventricle to the aorta by a parallel method, then you get the blood from the left ventricle, push it into the aorta, we call ventricular assist device. It's another artificial heart, a different type of artificial heart. What it does, it connects with some tubing to the left side apex of the ventricle, we call left ventricular apex. You connect a tubing there, connect it to a pump. The pump should have some rotating means to get the fluid and push it just like a fan, and then it pushes out into the aorta. So if this heart is not functioning, or heart has stopped functioning, or going to stop functioning, or in a very less way it is functioning, this device will take over. It gives the same amount of flow and same amount of pressure to assist. So the heart remains there. We are not cutting off and removing the heart from the body. It remains there. And this is called ventricular assist device, or it's an artificial heart for the failing ventricles. This is not total artificial heart. Total artificial heart is complete removal of the natural heart and putting this all together. But we are only assisting here. But the natural heart remains there. We put in one more heart, a parallel path. Okay. So what are the different configurations of this VAC? We can put in all the chambers. You put in the left side of your heart, in the left ventricle, we call it as left ventricular assist device. You put it on the right side, we call it as right ventricular assist device. You put it on both the ventricles, we call it as biventricular assist device. Both the ventricles. But the pressure and the flow and the power would be different. For a left ventricular assist device, it has to give the systemic flow and the blood pressure. For a right ventricle, it has to give the same flow rate, but 1/3 of its pressure. For a biventricular, it has to give the blood pressure, it has to give 2 blood paths. That is so the power naturally increases. So this is how the VADs have been configured. This device could be configured for different types of patients. And where exactly this VAD can be used, in what occasion it can be used. Now with this possibility, VAD can be used in 4 different stages. In the first stage, the patient, a dying patient having a end-stage heart failure, has come to the hospital or has been diagnosed with a heart failure which has no remedy. Then there is a possibility now, there is an off-the-shelf heart available which can be taken from the store, put it on the patient and wait for the decision. Now the clinician can wait. The clinician can take a decision on what is the next step. He's buying time. If he wants an investigation on, based on his current status of the natural heart, that you could provide some rest to the heart so that it naturally regains its form. You get fever, you get ill, you take a medicine, you sleep for some time, maybe after that you recover fast, right? You go to any other, you get any other disease, you take a medicine, you get sufficient rest, you come back, your health comes back. But unfortunately, you were not having that opportunity with heart. Now with this device, we are giving that opportunity. That is called bridge to recovery. There is a possibility of recovering the heart in the natural way by providing rest with the help of pharmaceuticals, with the help of medicine. So that's called bridge to recovery. And the third step is, so you cannot do anything with recovering the heart. The heart has gone, it has gone to that such a lower level. You need a new heart altogether. But the heart need to be available in your site, in the transplantation site. So for that, you need to wait. So this is called bridge to transplant. You put the device on a patient until the heart is received. It may be 1 day, it may be 2 days, it may be 100 days. In Australia, the recent thing what I have told, it was 100 days, right? So you could wait, it's called bridge to transplant. Now the fourth option is, if the technology is so mature and there is no donor heart, you cannot have a resurgery to remove the device and put a new heart. the patient is not willing or is not having that no kind of strength to do that, you keep the device as long as is possible. That is called destination therapy. Now my question will definitely come to your mind that all these things are possible, or does it really happen anywhere in the world? Yes, it has happened. So this has gone through nearly 60, 70 years of research all across the world. It started from the first generation, which is pulsatile, which I have shown earlier, the SAC, the first artificial heart, which is like a plunger with a small chamber. We moved from that technology into the second generation where you have rotation. So this rotation is like any pump, a water pump, an aquarium pump. It takes water because of centrifugal action, suction, and because of centrifugal force, it gives out that fluid. And now the third generation of pumps have come, LVAD has come, where we have incorporated a technology called levitation, magnetic levitation. I think your sister concern in Chennai itself is working on a technology called Hyperloop in IIT Madras. So what this Hyperloop works, it is to increase the speed of a train. But conventionally the speed of the train is limited because of track contact. Now you have got your rails, you have got your wheel, these are in contact. When you have something in contact, what happens? There will be friction. Friction will try to reduce the exerting force because of heat, because of energy dissipation. You cannot extend the speed to something more than that. Now any of the technology in transportation, the primary factor which enhanced efficiency was removing the drag and friction from it. You take the aircrafts, the efficiency has improved when you have improved the aerodynamics. Now in the Hyperloop, you are increasing the efficiency of transportation by removing the friction also. So what you have done in this Hyperloop, or what you are going to do in that kind of technology, is to create a non-contact movement. When you create a non-contact movement, thermal energy dissipation is removed from the system, the friction is removed from the system, wear and tear is removed from the system, your system will work in the same way it was designed, right? So if you can do the same thing in the artificial heart, then you can enhance the reliability of the system. That is the third generation device. This third generation device is magnetically levitated. The artificial heart is working in such a way that it does not touch anywhere. That's called magnetically levitated. Now we can see the complexity of technologies coming into the system. Now with this all third generation, now there are 25,000 people all across the world who have tried this technology. They are not living, all 25,000, but there were different stages of living. And the best case scenario was more than 10 years. A person lived for more than 10 years with the artificial heart. So what are those LVADs which people have tried all across the world? This is one of the LVADs which I have shown in 1969, 1970, the first left one. From there, the technology has enhanced, improved the device configuration and design to something like this, so very small. So over a period of 70 years, it could increase the technology and the landscape into something a lot low footprint technology. But unfortunately, these technologies are made by only a few countries in the world, especially from the western regions. We could not get that to India because of the exorbitant cost of this device. This would be one of the highest paid medical device. The cost of a device is more than 1 crore, the device itself. Then you have to get the expertise for getting that on a patient. So it's a very, very, very high cost intervention. It's not a simple intervention. It is not a low cost. You cannot simply go to a hospital and get it done. So what we have to do from our side, we have to create research and development approaches to build an artificial heart in India. So that program was started by Government of India a few years back, and we have been assigned the task of developing the left ventricular assist device and artificial heart in the country. So these are the design features that we would look into, the R&D approaches that anyone who is working in this area, who you can work also in this area. So what are the design features? It should have a continuous flow. It should create a sufficient flow as per the weight of the person. It should have the pressure, which is your blood pressure. And this blood pressure should not vary when you change the flow. That is one important factor. When you take any other mechanism, you change the throttle, you change the adjustment, the flow changes, the pressure also changes. But that should not happen. Your blood pressure remains constant, right? Your blood pressure is not changing. So So you should have an adjustable flow but not the pressure. And also your internal forces within your device should be so small, it should not break down your blood vessels. It should not break down your blood cells. That breaking down of blood cells are called hemolysis. It should not be so small also, so that the blood is not moving at all. If the blood is not moving, then the blood stagnates. When the blood stagnates, within 15-20 seconds, your blood starts clotting. So that also should not happen. And one other important factor is this: you should have your pressure and flow when you put it in a graph. Your flow and pressure, the graph should be like a perfect straight line or in a very near straight line. Most of the mechanical pumps which are developed, they will have a drooping characteristics. When you have a drooping characteristics, that means when you have more flow, you will have the pressure also reduces because of the losses, right? You know, it's there happening in electrical machines. You give some voltage, there will be a voltage drop, right? So this voltage drop is taking away the power which you are giving. So when you are giving that, we are thinking about the same way here. You are giving some power and some power is lost. So where is it lost? It is lost within your body itself. And that loss will have, this loss is temperature. This loss is thermal, temperature. So your device will heat up. If the device is heated up, you have a burning heart. That should not happen. So your research should be focused on making a perfect flat curve with the highest efficiency possible, so that very less drop is there. So what we can do on that, we have to remove the wear and tear possibility, whatever wear and tear happen on the system. There should not be any bearing, there should not be any friction at all. Remove everything from all type of friction happening on it. We have to create a motor which rotates this pump, and the motor should not have any sparking, should not have any, or at the possible, best possible, should have 100% efficiency. May not be possible in this ideal situation, but that is really required here. Because you cannot create cooling. You cannot have a forced cooling mechanism. You take your highest computers, they are having the best in class thermal kind of cooling mechanism provided. Radiators, heat pumps. You cannot have heat pumps and radiators here. Your indigenous technology should be as perfect as possible, that the heart is not heating up. The heart, your body, it's not heating up. The same way we have to create our organs. When it is working in your body, it should not vibrate. It should not create noise. You cannot feel the vibration of your heart. You cannot feel the noise of the heart. When you recreate it, the same thing, otherwise nobody will accept it. You cannot have when you start your engine, your car vibrates. You cannot have that when you start the heart. You should have a low noise, low vibration setup. Finally, you should have a controller, your best in control system, and the battery systems and the power systems, charging stations and all. So how is it possible to make? As I said, there is a requirement of the pressure and the flow. Similarly, if you want to make all these things like no friction, very good motor technology, low vibration and noise, you have to separate the motor and the pump as an independent unit. But at the same time, it should work also. You think about a pump coupled to a motor. How is it coupled? It is coupled through a shaft. The shaft is a driving mechanism. The motor has got an armature. The armature rotates, or the rotor rotates. The rotor converts that kind of transmit the torque from the motor to the pump, which actually does the mechanical job through a shaft. This is happening everywhere. In an automobile it is happening, in a crane it is happening, in a water pump also it is happening like that. But if you do the same technology, if you incorporate the same technology here, what happens is, when the motor starts functioning, the whole system vibrates. The movement is translated. So you should create it in an unconventional way, which is not like the electrical machines. If somebody from electrical engineering is there, they will say that the air gap in the motor should be as low as possible. The air gap, when it is as low as possible, the efficiency increases. But here we cannot have that, because air gap, first of all, there should not be any air. Second thing, the gap we have to deliberately introduce as a cushioning. Does not have directly connected. So, what is the real mechanism that we have to build on, or we have to work on? So, three major problems I would suggest. These are the design challenges. The design challenges are on the hydrodynamics. We have to create a bearing. We have to create a 100 mm average pressure without changing when the speed is changed or the flow is changed. And we should avoid any bubbles forming on the blood flow. And the second, which we are more interested in, is the engineering. There is a control, there is a balancing, there is a size. The smallest size is always the best. It should be a temperature. If there is a limit of 37 degrees Celsius, the maximum could not go beyond 40 degrees Celsius. And the power, it should not be more than a conventional light bulb can take. 15 watts or 10 watts is the maximum power. Should not take more than that. We can solve all these things as engineers, but something which we cannot solve is the tricky part. That's called hemodynamics. The properties of the blood. Blood is a living thing. You put it in a pump and you rotate it high speed. Don't think that the blood will remain as a blood. The blood changes its properties. That change in properties happen in two different ways. One is called hemolysis, which is a damage of the blood cells rupture. The hemoglobin comes out. And that is going to act like a military. You get invaded by a foreign military, then immediately your military system will automatically activate. It's like the Israel's Iron Dome. It activates by itself. It's called autoimmune. You get your one of the blood cell damage, the proteins are released. That protein will tell the remaining blood cells to counterattack. And that counterattack will be a catastrophic effect. It's something like you get some bacteria or virus, your body heats up. The same way. And if it happens for a long time, then the problem continues and it starts coagulating. This coagulating will manifest as a thrombus, blood gets clotted together. When this clotting happens, in the engineering problem, you have got reduction in pressure and flow. You cannot now maintain the pressure. So the design methodology should be to create a pump with all the features to make a very good system with nice engineering playing there. You should have a motor which with all the best in physics of electromagnetics, but at the same time it should be immersible in a conductive fluid. It should not create a short circuit. It should be able to work with blood. It should be in an immersible condition with blood. And it should have a non-contact, frictionless bearing technology. And finally, we have to test it. In what way we can test it? We need equivalent systems for testing it. And finally, just to go through standards, guidelines is provided in the ISO standards to meet as per the international parity. Whatever has been produced by the world's best, we also should recreate the same thing. In blood, first we have to do in blood, then we have to do in animals, then go to the human. We go through first in silico modeling. We find out the velocities of blood passing through this mechanism, the shear rate and the forces happening on the blood, and see whether all these forces fall within these values. These values actually trigger the hemolysis and thrombus. If you can find out your design so that these three factors are being prevented to trigger, then I would say that the machine will start working. Then we have to find out the systems when it is operating, what is the velocity of operation. You cannot have a very high velocity, you cannot have a very low velocity also. The velocity usually falls between 0.5 meter per second to 5 meter per second. That is the maximum velocity and the minimum velocity which is there in your body. So if you want to create an equivalent system, that system also should have the same velocity. It should not speed up immediately, it should not slow down immediately. All the blood paths within it should have a velocity within this region. Now frictionless bearing is of very high importance. As I said, friction causes wear and tear. At the same time, the direct contact creates temperature rise, the thermal release. So if you can create a frictionless bearing, that would help you to solve the problems like heat generation, definitely. Then the hemolysis, that is blood damage, wear and tear, and that vibrations because of wear and tear, everything could be solved. And one of the major problems is there will not be any particles coming into the blood, because those are all foreign materials. Foreign materials should not come into the blood. So these things can be solved. So when you look into a conventional rotating structure, an ordinary a top or something, an impeller or rotating structure, when you want to rotate it in a stable way, what do? You have to make it arrested in pivots. This is a conventional method. But when you start arresting in pivot, there is a point called pivot here, there is a contact. So this region start wearing out. This is what I said, wear and tear. So this wear and tear induces particles into the stream. At the same time, thermal energy also starts coming out. So there is a possibility now. Magnets are there. It can be best utilized to create a levitation. And if you can levitate it, then you create a non-contact structure. So this is a non-contact structure. Ideally, this should be the case. You should be able to run the machine without having any direct contact with any of the solid walls. Okay. How is it possible? It is possible by having a series of magnets. Simple thing. We know magnets repel each other, magnets attract each other. We can make use of magnets for creating magnetic levitation, as I have said in Hyperloop or in French TGV or magnetically levitated trains and all, world over. But there is a problem for that technology also. What's the problem? When this is magnetically levitated, a brilliant scientist has already found that you can levitate it only in one direction. You take one magnet over the other, you can see that the repulsion happens in one direction, it immediately try to fly away. So that means it gets stable only in one direction. Earnshaw, it has been proved that it is not possible to achieve the static balanced levitation in all the directions put together. You cannot have the levitation in 3 dimensions. You can have in 1 dimension. So that there is a physics limitation. Okay. So how we can solve this? A combination of, so this really becomes important when you have lateral forces. You have something rotating like this, when there is a small disturbance, it flies away. So that's not an ideal situation. You cannot always ask the person to be correct, vertical. He has to lie down, he has to move, he has to bend. So it's not possible. So at least 1 degree of freedom we can arrest like this. What about the other degrees of freedom? There are 2 more degrees of freedom. What you can do for that? We need innovations, inventions in bearing technology. So this invention is a combination of 2 principles. One is a magnetic principle and other one is a hydrodynamic principle. So these principles, when it combined together, you can see here, we are providing some channels of blood to pass through your spindles, your gaps within the system. These channels of blood will push the rotor and will try to create gaps. This method is called hydrodynamic method. So using this hydrodynamics, that means we are trying to get the forces of the fluid itself to act like a bearing. So that has been used along with the magnetic bearing to create a combination, and this is a new invention in that. It's called hybrid bearings. So this hybrid bearing helps the artificial heart to work in a non-friction, non-contact manner. That has to be proven. You can see here in the computational fluid dynamics, we could see a very narrow channel of fluid being passed through the rotating structure. In between the rotating structure, this small channel. This channel helps to stabilize this system when it is operating. It needs a very fine feedback control. This feedback control gets the information like speed, flow and pressure, and then controls the system. Now finally, with all these techniques put together, this is the first artificial heart developed in our country by our institute. You could see that so it's the beginning of a long story. It's just the prototype. This picture is only the prototype. It's a static model. You have to make it work. You have to test it. You have to prove it. So that's a very big challenge. Prove that system. Prove the technology. As I said in the beginning, it has to go through many different stages of testing. This is a complete setup. It consists of a smart controller. We call it a Chitra bag. There is a device made up of titanium. It's magnetically levitated. It has got the best performance in comparison with any of the devices in the world. We have got a series of batteries and battery packs and controllers. We have now made multiple prototypes. We have tested. We created the entire loop of testing in our facility. I would welcome you, your students. You can all come to our institute and see this system. It's working a lot. We have made a complete data acquisition system to see how we acquire the data and do the real-time analysis to understand how it is working. Now this is all as per our international standards that we have to make. We do that, and now we get the comparison. Now to make a device working in India, where we want to claim that it is an Indian product, you should not simply say that no, we have worked on the problem, we created the technology. No, that is not sufficient now, because India is a rich country now. It's going to be a 5 trillion economy. You have opportunity to buy technology, right? So you can get a technology from US, Germany. You can get a technology. So if you want to make the technology and make it a successful thing, you should have the same performances of what is available in the Western world, what they have reached. When you reach in the same level, then you try to enhance it with additional research, That's a perfect solution. So what we have done is, this is a comparison of two artificial hearts. The blue line shows one in India, developed by us, and the red one shows one by US hardware. It's by Medtronic. If you know about Medtronic, Medtronic is a very big company in the world, medical company in the world. So this shows the comparison. This gives you the information about how, in the engineering perspective, how it works. But engineering is one out of the three segments. We have to look into the other areas as well. This is the beauty of levitation, what we have created. You can see the system being levitated. You can see it is rotating without having a direct contact with anything. You can see now the fluid coming inside. You can see that there is no contact here. It is moving without having any contact. So that's the technology which is playing within that small device. In a few moments, the blood will start coming, and so the water we have created here to see, and it circulates. So we have this imaging techniques to understand what is happening within the pump. This is how it is going to pump the blood when it is really working. So moving forward, we have to do the thermal analysis and see whether it is creating temperature more than 40 degrees Celsius, because body can accept till 40 degrees Celsius. You cannot be more than 40 degrees Celsius, because it will burn out, problems will come, then necrosis will come, the tissues will damage, the nerves will not conduct when it is more than 40 degrees Celsius. So that has to be extensively studied. And studies mean you don't continue studies on a physical model, you have to make a computer model. So we have done the computer modeling and then tested. So our computer modeling says that the maximum surface temperature will go to 39.8 degrees Celsius. The accuracy of this computer model need to be first qualified and validated with a lot of mechanical systems, and finally you have to test in the real system. So this shows the real system data with blood. The real system data shows that you have got results like 39 degrees Celsius even after 6 hours. That is what the result says. So that is we are becoming closer to the device in its perfection to take it to the human level. The next important thing is like whether your device will it changes its performance with time and with respect to your body. For example, you are standing at one performance, you are walking in a different performance, you are sleeping a different performance. That's not good. That's called sensitivity. How is the sensitivity of the device? So we have taken, with respect to human heart, all other artificial hearts tried across the world, and then compared our device. You can see the Chitra artificial heart. We have compared with all the available hearts in the world, and then you can see the results. The best of the technologies like HPAD and HeartMate 2, we have got very similar results to them, 0.067. That means now we are one step closer, and we have got a communication technology. Okay, everybody knows that. And now we go to the blood, the second phase of testing. In the blood, we find out whether the blood will have damage or not. There is an acceptance criteria. Below that acceptance criteria, we can take it forward. That is also compared with the Berlin heart from Germany, the HeartMate 2 and HeartMate 3 from America. We have compared that technology and do the reliability testing. At least for 100 days, the device should work. So we do the testing for 100 days continuously, monitoring it, sleepless nights. We give the data acquisition, media acquisition, and all the multiple people stand, find out each and every parameter, 20 parameters, keep on monitoring and see what really happened on the system during its 100 days of operation. That has been tested, and the laboratory test shows that there were no adverse events, and this gives the permission. This is the data that we have to give to the regulatory agency to get a clearance to go ahead with animal trials. Without this, they will not accept it. So this has helped us to move forward, and to start fabricating the device in a clean room. So this is a clean room facility. We started fabricating the device. These are the multiple models which we started fabricating, and you can see the very first data information which I said it should be within the water. It should work. It should not have a problem when it is immersed in water. So that has been proved, and all. We move forward with animal evaluation. So this is a real animal which lived with an artificial heart, and we did it internally in our facility, and we test the animal and we observe the animal for 3 days and see the problems of the animal, which help us to move forward and all. So this is the system. If it works, let me see if it works. Okay, no problem. We'll see later. Okay, so these are the real experiments on animals on really how this device works. You can see this is the patient is an animal. This is the heart portion. We get connected to the heart, and then you can see this is the LVAD. The surgeons are operating on the LVAD. This is the artificial heart. So, but it's not so simple system. It's a very complicated instrumentation. This is the complete setup. You have got your animal in the center. You have got your LVAD here. You have got the controllers here. You have got all the data into the system. You have emergency backups, ventilators, all cardiac resuscitation systems and all. You can see your LVAD here. You can see your animal here. So, what is to move? What is to come? Now, what has to come is, why science still has not cracked the artificial? Why are you not seeing a person walking around with artificial heart? There are a few more things that we have to work on. The research in progress is to see, can it be made as equivalent as that of a heart by pulsatility? Can we create the artificial pulse? For creating the artificial pulse, you need to switch the motor. You need to switch the motor to turn on and turn off in 800 milliseconds time, because that's a heart rate current. In 800 milliseconds time, you have to turn on a machine, turn off the machine. And it has to happen every time. So this is the complication. So this is the second part of my talk, challenges. Second thing, if you want to be like so dynamic with the artificial heart, an athletic kind of a lifestyle,